Hello, everyone. Welcome to our continuation of blind search methods. So in the previous video, we did look at breadth-first search algorithm. So now we'll look at the second common algorithm, that is the depth-first search. So in the previous algorithm that we looked at, the breadth-first search, what we were doing was we are going through the search tree level by level. So when we look at the root, if it's a go, we report the go, that it's a go. If not, we continue to the next level. After considering the next level, if we don't find a go, then we consider their children. So that's how we were doing it. Now, in depth-first search algorithm, the way we do the search, the way the agent is going to go through the search tree is it will go branch by branch. It will go all the way down to the leaf nodes before it tries the next branch until the goal is found or until the entire tree has been searched. So if I may just use this this search tree, So in breadth-first search, remember we are going level by level until a goal is found. In depth-first search, we'll go branch by branch. So we start with one branch. If we find a goal, we stop. If not, we consider the next branch until we find a goal. So we are going to do an example so that we will now try to consolidate what this means. So depth-first search, we are saying we are going to search all the way down to the leaf nodes. So we'll go through the tree branch by branch until we get to the bottom of the tree before we try the next branch, just like that. There are advantages as we're going to discuss this. Don't worry about things like memory complexity. That is something we are going to discuss later on. So the pseudocode for depth-first search, what we do is we initialize the queue with the states. We're going to create a list of all the states that we have. And then we are going to get from our state space, we are going to get the first element of queue. So as long as the queue is not empty, we are going to get the first element of queue. If that element is the goal, we report success and we stop. If not, we are going to expand the children of Q1. And when we expand the children of Q1, we are going to eliminate the children that represent loops. The remaining children, we are now going to put them in front of Q. So we execute the Q from front to back. That's how we execute. In breadth-first search, what we are doing was we would consider the sibling nodes. So siblings, nodes that are at the same level are what we are referring to as siblings. So we consider the siblings before considering their children. In depth-first search, we are doing the opposite. Consider the children first before considering the sibling of the parent. That's what we are trying to do. So quickly, we are going to look at an example. So this is the same state space that a state space we are looking at. So now we'll try to navigate to show how the agent will navigate using the depth-first algorithm. So let me just open a whiteboard. Okay, let me just open a whiteboard quickly, and then we're going to work out an example together. So just give it a second while it's while it's loading. Okay. Okay. So I'm opening the board. All right. So quickly, let me just clean up these things. Okay. So depth first search algorithm. Remember, we said start with the first element. So in the in Q, you are going to have all these states, the state space. That's what you have. So get the first element of of Q, which is the initial state in this case. So we have A. Is A the goal? No, it's not. So what do? We are now going to expand A. So now when we expand A, we are now looking at who are the children of A. There is Sibyl, and there is Zirind, and there is Tim Zora. So this is Tim Zora. Okay. Then this is Zirind. Now, these two children of A, you notice that I've put them in dotted lines. Why? Because remember we said in depth first search, we are going to go branch by branch. So the first branch we are considering is this one. After we exhaust this branch, that's when we'll go to the other branches if we don't find the goal along that path. So from S, we check, is S the goal? No. What do? We now expand S. Now, when we expand S, so from Arad to Sibyl, when we expand S, there's Odaria, Farara, and RV. So again, we are assuming we are going alphabetically. So if we list these alphabetically, we have Ferrara, then sorry about that. Okay, so we have this one, and we have RV. Sorry about the writing, don't mind. So now, when we expand like this, we want to go branch by branch. So we now check the children of the first child of S, or is F. Is F a go? No. So now we expand F. We now expand F. Now, when we expand F, F just has one child, and that is Bucharest. Is Bucharest a go? Yes. And then we report success and we stop. So these solid lines are the nodes that we have expanded. The ones that are dotted are yet to be expanded. So, sorry about that. If we are to list the towns we have expanded, we have Arad, we have Sibiu, we have Ferrara, and we have Bucharest. So this is the path that we would take. So this is how we would conduct depth first search. So in breadth first search, we are going level by level. But in this case, we are going we're going branch by branch. So if we didn't find the goal on this branch, we could have backed up here, then consider the other children. So I think to show how that is done, we'll do another example, just to just to show how this is done. So this is how, first of all, we did it. So now let me close this whiteboard, and then we'll look at how that. Okay, so having looked at that example, let's see if we can consider another example. So this is a question that I want us to try out. The question says, consider the following graph representing the state space and operators of a navigation problem. The details we have been given is S is a start state and G is a go state. When we are expanding children on a queue, assume that the children are placed in alphabetical order. And then we also assume that we never generate children that appear as ancestors of the current node. So we avoid loops. So the questions that we want to consider are: one, what is the order that breadth first search will expand the children nodes? And what is the order that depth first search will expand the nodes? So since we are considering depth first search, we are currently considering depth first search. Let's start with that one. So we'll try to work it out on here. So we'll try to first of all show how depth first search will expand this. So remember the pseudocode. It says you list the state space in Q, and you get the first element of Q. You check, is it a parent, is it a go? No. If not, then you expand its children. So S is not a go, so we are going to expand the children. Now, the children are supposed to be placed in alphabetical order. So meaning we start with A, since the children of S are A and B, so we have A. This one, I'm going to put dotted lines. And the reason is we are going branch by branch until we get to the end of this branch. That's when we'll come this way. So when we come here, uh, we check, is A the go? No. So now we expand A, and the children of A are going to be put in front of B, meaning they are going to be considered first before the sibling of A. So in A, the children of A that we have are B and D. So let me just write this and then show. So one concern that we have is, how come B is a child here and D is a sibling here? We are looking at the paths. The first path, we started from S, B. This is the path here. The other way of getting to B is we go from S to A to B. So we are going to list this as a child because we can reach B through A. Now, we check, is B a go? No, it's not. So these ones, B, D, and B are in the list because they haven't yet been considered. Remember, we talked about the concept of open nodes and closed nodes. So S and A are closed nodes because they have been considered. They have already been expanded. The ones that are yet to be expanded are now kept in the open list, and they are ones that we are looking at. So we've moved from S to A to B. So S to A to B. So when we are here now, we have to look at who are the children of B. From B, where can we go? So from B, we can go to C, and we can go to E. Sorry about that. Okay, let me just clean it up. Um, okay, so that's B to B to E. I need to, B to E. So we have now moved from S to A to B, B to C. So S to A to B, B to C. So when we're in C, C has only one child, and that is H. Now we ask ourselves, is H a go? H is not a go. So now we are going to move one step back and look at, first of all, H is not a go. Does H have children? No, H doesn't have children because it's a leaf. So we go back to the previous node, which is C. Does C have another child? No. So we move up again to B. Does B have another child? E, yes. So to show that this is now expanded, I've decided to put a solid line. So deliberately, I kept this so that you now see that at this point we are now expanding E. Okay, so since we are now expanding E, I'll quickly get rid of this and then just have a single line like that. So we are now expanding E. So now, how did we get to E? To SABE. SABE. So when we are in E, the children of E, from E, we can go to B, to D, and to F. So we can go to D, or we can go to F. Since we are going alphabetically, we go to D. So how did we get to D? We moved to SABED. SABED. So when we're in D, which children, who are the children of D? Now, remember there's that condition, the second condition here where we said, do not expand children that appear as ancestors. So because in this path, A already appears, it cannot appear as a child of D. When we move to SABED, A has already been listed. So the only child of D that we have, which has not been listed, is G. So the only child of D that we have is G. And then we ask ourselves, is G a go? Yes, G is a go. So normally, when we are creating these trees, we put this as nodes. Unfortunately, since I'm using my computer to draw, that's how come I'm just writing the letters to simplify it. But when you are answering, these nodes should be clearly shown. So having expanded this, the next question we were asked was, show the list, the order in which these will be expanded. So now let us list the the states that have been expanded. We started from S, then we went to A. From A, we went to B. From B, we went to C. From C, we went to H. From H, after getting to this end, we came back here. So these have already been listed. So after expanding this, we went to now E. Then we went to D. And we finally ended in G. So that is a path that we took. So this is another example of how depth-first search will expand or will search a state space. So thank you very much for listening. So we've now looked at the two common methods of blind search, which is depth first and breadth first search. Of course, there are other methods. There's a uniform cost search. There's hill climbing methods. There are just there are a number of them. So for the sake of CS471, we'll just consider these two as a starting point. If you have to use a different algorithm, at least you have the basics you can build on from here. Thank you very much for listening. Obviously, you can try out and see how you can expand this or how you can construct a search tree for breadth-first search on your own. Thank you very much for watching. In the next session, we'll start looking at informed search methods.